Hi, today we're going to start working on chapters 8 and 9, and I like to cover these kind of together because I like to take some topics from 8 and some topics from 9, because they kind of go, I kind of like to rearrange the order. So we'll be skipping around a little bit. So we're going to be looking at chemical bonds and molecular geometry. So in chapter 7, we just learned about valence electrons and how to count them up, and we learned that those valence electrons are the ones involved in chemical reactions and bonding. And so we're going to use that knowledge to start drawing structures. So we're going to start drawing Lewis structures and predicting three-dimensional structure. And just to convince you that this is important and that you care about this, the structure of molecules tells us a lot about how the molecules behave and interact with other molecules. For example, structure plays a huge role in how drugs work, like sticking to an active site of a biological molecule to inhibit some behavior. So one that you're familiar with are NSAIDs. NSAIDs are non-steroidal anti-inflammatory drugs. So this would be like ibuprofen, Aleve, things like that. So these are COX-2 inhibitors. So this is how they work to prevent pain. The COX-2 is an enzyme that's activated at sites of injury. It manufactures hormone-like substances called prostaglandins, which trigger painful inflammation. So you can see your little COX-2 guy here. Then the prostaglandins are these little things here that make pain. You take your COX-2 inhibitor. They're designed to block the activity of the COX-2 enzyme. So it'll put this little horseshoe thing around it so that it can't release those prostaglandins anymore. But of course you all know that if you take too much ibuprofen that it can have some negative side effects, and that's because these prostaglandins have other mechanisms as well. So over here, this prostacyclin, produced by COX-2 in blood vessels, opens blood vessels and prevents platelets from clumping. So if you take your ibuprofen, it's both going to relieve your pain and it's also going to reduce your ability to open those blood vessels, and you're going to get some clumping, maybe. So researchers believe that when COX-2 is blocked, prostacyclin may also be suppressed, allowing platelets to stick together, and the blood vessels can constrict, which can lead to heart attacks and strokes, which is, of course, unwanted. So understanding the structure of molecules is very important so that we can understand how things work and we can design drugs and understand how our bodies work and all these things. And that all depends on shape. So not just knowing the formula, like that it's C2H3O2, but actually how those carbons and hydrogens are attached to each other and what their three-dimensional shape is. So we are now going to learn how to predict the three-dimensional shape of molecules. All right, so to learn how to predict things, we are going to use what's called a Lewis model. So we're going to represent electrons as dots and draw Lewis structures. So we discussed valence electrons already in the last chapter, being involved in bonding. So we're going to need to keep in mind those electron configurations. So let's review the electron configuration for carbon. So remember, we fill the 1s2, 2s2, and then we're going to look at carbon on a periodic table, and it's 2 into the p's. So how many valence electrons do we have here? So recall we're going to look at only the ones that are in that highest principal quantum number, and we have a total of 4 valence electrons. So when we're building molecules, we're going to have to be able to count up the valence electrons for each element, and then we're going to be able to draw Lewis structures from there. So the Lewis structure for carbon So the way we draw a Lewis structure, we have a C, so you just use the symbol from the periodic table, and then we're going to put 4 electrons around it. So we usually can put electrons, we can put 2 on the top, 2 on the left, 2 on the right, and 2 on the bottom in total. So first you're going to put them singly, and then you can double them up. So just like that rule where we wouldn't pair up the electrons in the beginning. So let's try a few more of these. Let's draw some more Lewis structures for single elements before we start looking at other ones. So let's draw a Lewis structure for sodium. So we know we're going to write down the symbol for sodium, which is Na, and then we're going to take a look at the periodic table and find sodium, and we'll find it right here. And you can see that sodium is going to have just 1 valence electron because it's going to have that 3s1 right there. So we just put a little dot. Then let's draw a Lewis structure for chlorine. So we're going to use our symbol for chlorine. Look at the periodic table and find chlorine. It's over here. So the valence electrons, you just count across here. 1, 2, 3, 4, 5, 6, 7. So we go 1, 2, 3, 4, 5, 6, 7. All right, now let's try krypton. Krypton is a noble gas, and we know that all noble gases have a complete octet, which means they have 8 valence electrons. So krypton has 8 valence electrons. So a complete valence shell is most stable and called an octet. So oct meaning 8, that means we have 8 electrons, and that's what everybody is trying to achieve. Everybody's trying to look like a noble gas, all right? So think of those, they're like the cool kids, the noble gases. Everybody wants 8 electrons. So everybody's trying to get that complete octet. So let's talk a little bit about bonding, chemical bonding. So a chemical bond involves transferring or sharing electrons. And then we can have different types of chemical bonds, which we've already talked about in this semester. We talked about which types of compounds transfer electrons and which ones share electrons. So remember when we talked about ions and ionic compounds? So those guys do not share, right? The anion steals the electron and the cation gives up an electron, and then they're held together via electrostatic interaction. So electrons are transferred in an ionic bond. In a covalent bond, electrons are shared. So that's like our molecular compounds. And then in a metallic bond, these guys are kind of different. We have what's called a sea of electrons. So the electrons are delocalized. Creating a sea of electrons. And that's one reason why metals are so good at conducting electricity, because those electrons aren't really, they don't have to stay on any particular element. So that electron flow is actually where you get your electricity. So these are our different types of bonds.